Hey guys, good. How are you?
Good.
You guys are the first.
Oh, howdy.
Hey guys.
Yeah. This building. That's how it's got. My hearts. Yeah. How's it going, Professor?
Oh, just relaxing. I just chilled out.
Yeah.
How about you guys?
It was very fun.
You guys go out?
Yeah.
Nice, nice.
After Ansys project, of course.
Mm.
Of course. Let's get it, bro.
How's your Halloween?
Hey.
Dr. Tran, are we jumping into week 11 notes this week?
We have a little bit more on the beam notes to finish up, and then I think probably that'll probably take us most of today actually, and then we'll jump into the transient stuff after that.
Dr. Tran, quick question. Hi, by the way.
Hey.
Hey.
Yep.
So if you want to just find the reaction forces for each of these systems, truss, beam, we need to use the element stiffness matrix, the global stiffness matrix before applying the boundary conditions and multiplied by the I think it's like use the deformations, right?
Yep,
Okay.
exactly.
Yeah, I just wanted to make sure. Thanks.
MATLAB is your friend for those.
Wait a second. Oh,
I said
MATLAB. Yes.
MATLAB was my friend for
Oh,
that.
most definitely. Yes.
Took me a minute to work the code out right, but oh, it's such a good feeling when you
Mhm.
plug it in and you realize it comes out right. The weird thing with MATLAB though is it keeps giving you like these exponentially small numbers or whatever times 10 to the negative 16th or something like that.
Uh-huh.
And I have to change in between like format short and format short G or format bank in order to make sure the numbers come out a relative small size.
Oh yeah. That's one annoying thing. The reason for that is MATLAB solves those systems approximately, so they don't find a direct solution. And so sometimes you get something like that where it's off by like machine precision, basically. Will I be teaching 401 next semester? I don't know. That is a great question that I don't know the answer to. I don't know what I'm going to teach until probably at least after Thanksgiving, maybe even closer to Christmas. Yeah. Okay, it's 5:30, so let's go ahead and get started. All right, good evening, everyone. How's everyone doing today? We're on the eve of the project due, or I guess not the eve, so we're just hours before the project's due. So I've seen that quite a few people have turned it in already. So thank you everyone who's turned it in early. But for everyone else, just make sure you get it in before midnight because I think the submission actually does close at 11:59 tonight. So make sure you finish that up. Okay. If you have any last minute questions on the project, I'll be sticking around after class today to answer them. Or you can send me an email tonight too, and I'll try my best to get back to you. Okay. All right, and so the plan for today is we're going to finish up our lecture notes on beam stuff. Okay, and so after the lecture notes today, you should be good to go on everything on the problem set. Okay, so for those of you who have started, it is quite the doozy of a homework assignment. So make sure you're working on it. Okay, I believe the due date for that is going to be next Friday. And so, if you've been focusing on the project this whole time, you still have about a week and a half to finish it. So, I would definitely get started on it sooner rather than later. Okay. All right, question. So when will the midterm review video be posted? So the midterm review video, I plan on recording next Friday because our midterm is not next week. It's going to be the week after that. And so I always do the midterm review video, the Friday before the midterm week. And so next week I'll put out a poll. I'll put out a study guide in a poll next week. Where you can you can vote on the midterm topics, and then you can and I'll record the video next Friday. Okay. All right. I think that's it. So the other thing we're going to do this week is we're going to prepare for our next ANSYS activity. And so it's been a while since we've done ANSYS activities, although probably you guys have been working on it this whole time because you've been working on the project. But right now my plan is for next Tuesday to be our next in-class ANSYS activity. And so we have a little bit of stuff to cover before we get there. And so, before the end of the week, we're going to be covering those lecture notes. Okay. All right. So I think that's it for my announcements. And so are there any questions I can answer before we formally get started?
That midterm review, is that an in-class thing or are you just posting that prior to class?
So I'm going to record it next Friday and I'm just going to post it on YouTube. And so it'll be outside of class. Okay. Yeah. Mm-hmm. All right, so there's no more questions. Let's go ahead and get started. Okay, and we are in the middle of covering beam equations, right? So this is the very end of our unit on the direct stiffness method. Okay. And so throughout this whole unit of the direct stiffness, we've been working on solving these finite element problems essentially by hand, right? And so we've been I've been giving you guys a system comprised of several structural elements. You've been forming the element stiffness matrices of them, assembling them into the global system, applying boundary conditions, and solving. Okay. And so, there's really not much more we can do to comment on that process. We've kind of done everything. The only thing that's left to do is to cover one last topic in terms of distributed loading. Okay. Okay. And this is another topic that should hopefully tie together, what we've been doing in ANSYS and the hand calculations. Okay. Because up to this point, if I can draw like a simple beam right here. Okay. So let's say we split the beam into these areas. So let's say that we have a roller support here, fixed support here. Okay. So we have a simply supported beam. And where I've broken up the beam, these are going to be the nodes in our system, and each of those segments are going to be each different beam element. Okay. And so up to this point, we've only dealt with cases where our loading is applied directly onto the nodes. Okay. And so let's say that we have two loads on this structure. Okay. So let's say we have a load on that one and a load on this one. Okay. And we'll say that they both have a magnitude of P. Okay. Right. So when the loads are applied directly to the nodes like this, they're very easy for us to insert into our direct stiffness system. Okay. And in fact, the way that we do it is that, once we have our global stiffness system, we just insert these P's, or we just insert these loads into the appropriate row on which it's acting on. Okay. Okay. And so that's all that we've been doing so far with these hand calculations, right? But we know, just through our experience with ANSYS, is that we don't often have loads that are applied at nodes like this, right? And so what we have instead are situations that are more like the following, right? And so let's say that we have the same beam. I'm going to break it up in the same way. Okay. What we have more often are cases where our load is distributed over a certain region of space, right? Okay, so what we have more commonly is something like this. Okay. Right. And so, if we go in ANSYS and we supply a load, oftentimes we're selecting an entire surface. Rarely, sometimes we can select an edge, and then very rarely, we apply the loads at a point, right? But most of the time, we're applying a load on a surface like this. Okay. And so, we've kind of been using this with ANSYS without really thinking about, what's actually going on, right? But if I gave you a problem like this right now, and I told you, solve for the deformations in this beam, right? Given that, I have this load function, let's say that it's a function of X, arbitrarily, right? We wouldn't be able to solve this yet because, we don't have these loads that are applied at the nodes, okay? And so before we can actually solve this with the direct stiffness, we need to take this distributed load and convert it into an equivalent set of nodal loads. Okay. Okay. And so that's what we're going to spend most of the time doing today is learning about how do we take a distributed loading like this, where we have a load, spread out over a region of space, and how do we convert that to loads that are applied at the nodes, okay? And so, underneath the hood, when you apply a distributed loading in ANSYS, whether it be a force or whether it be a pressure, right? And we apply that on an area, ANSYS is also doing this exact same procedure. Of course, they're doing it much faster because it's a computer. But in order for ANSYS to solve a system with distributed loads, it needs to convert these to nodal loads first, okay? Because otherwise, they can't insert that into the global stiffness system. Okay. All right, and so we're going to learn how to do that today. And I'll tell you, it's not the most fun process. It's a little bit tedious, but you'll see how this is done. Okay. All right. Any questions on this? Okay. All right, and so how are we going to go about converting these loads? And so the way that we're going to convert them is through a principle called work equivalence. Okay. Right. So hopefully everyone's familiar with the concept of work, right? And so if you have a box, right, and you apply a force on the box, and then as a result of you applying that force, if the box moves to some certain distance d, right, then the work that you performed on this box is equal to the product of the force times the distance that it moved, right? Okay. Right, and so that's work. Applying a force that causes some kind of deformation or some kind of displacement is work. Okay? And work has units of energy. Okay. Right, and so whenever you apply a load onto a structure, and that load causes the structure to deform, you can basically say that load is performing work. Right? Okay. And so what was the last activity that we did? We did the bridge activity last, right? And so for the bridge, when you apply the pressure load on top, right, and that causes the bridge to kind of cave in on itself, what you can say is that the force, the external pressure, is applying work on the bridge. Okay, and so we can say the same thing for simple beams too. Okay, and so when we apply, and so let's say that we have our beam. Okay. I'm going to do a simple beam this time. And so let's say that we just do a single node in the middle. Okay. And we apply an external load here. So let's say that we apply a nodal load P, okay? And that gets the beam to kind of cave inwards on itself, okay? This is heavily exaggerated, of course, okay? But I exaggerated just to highlight this, okay? And so if our beam here deforms by an amount d, then what we're saying essentially is that our load P here is performing work on this beam, okay? And the amount of work that it performs is the product of the load, of the force load multiplied by the deformation. Okay. Okay. And so why is this important? So why are we reviewing this concept of work, right? And so, ultimately what we want to do is we want to take a distributed load on the previous page and transform it into a set of nodal loads, right? Okay. One way that we can do this is by saying that the distributed loading that we have, when we transform it into a nodal loads, those two systems, right, they have to perform the exact same amount of work. Okay. Okay. Right. And so that's that has to happen, right? And so it has to perform, basically the same amount of strain energy that the distributed load is causing. Your equivalent nodal loads have to do the exact same thing. Okay. And so we're going to use this principle to mathematically form a relationship between, our distributed loading and our equivalent nodal loads. Okay. All right. Any questions on this? Okay. All right. And so with that in mind, let's come up with a mathematical expression that expresses the amount of work done by a distributed load and by a nodal load. Okay. All right, so let's start with distributed first, right? And so for a distributed load, let's say that we just have a single beam element, okay? Okay, and so let's say that we have a distributed load like this, okay? And we leave the form arbitrary for now, and so we say that it's W of X, okay? Okay. Actually, that's really poor terminology. Let me change this to P, just because we're using W for work. Sorry about that. Okay, so let's say that we have a P of X, okay? The work that this distributed load performs is going to be the integral from x1 to x2, okay, where this is node 1 and this is node 2 on this side, okay, of the distributed load P of X multiplied by the deformation dx. Okay. Okay. Where P of X here, that's our distributed loading, and this y of X right here, this is the transverse deformation. Okay. And so we have this integral expression here that that computes the work for us. Okay. All right. So now let's look at how we can compute the work done by a nodal load. Okay. And I'm going to do the most general case where we have, we can have a transverse load and also moments applied at each node in our beam. Okay. Okay, so same thing as above, we're going to have a 2-node beam. And so we have node 1 on the left, node 2 on the right. Okay. Right, and so since we have loads being applied at the nodes, we're going to have F1y, F2y. Okay. Since we have beams as well, since we're on beams, then we also have the moments that are being applied at the nodes as well. Okay, so we have M1, M2. Okay. Okay. And so to get the work performed by these nodal, another way you can say is by these concentrated loads, we can just take the product of each of these loads and the deformation at that node. Okay. And so let's start with F1y. Okay. And so if we take the product of F1y and U1y, that's going to give us the work performed by F1y. Okay. Similarly, we can take the work done by F2y by multiplying it by U2y. Okay, so we have F2y multiplied by U2y. Okay. Right, and then we have the work performed by the moments. And so we have M1. Okay. M1 is going to cause a rotation at the node theta 1. Okay. And so the work done by M1 is going to be M1 theta 1. Okay. And then we have the work performed by M2, which is going to be M2 theta 2. All right. Okay. And so by our principle of equivalent work, we have two expressions here for work, right? So we have one expression for work which uses the distributed loading, and we have another expression of work that uses the concentrated ones, okay? And so, our principle of equivalent work says that these two have to be equal, okay? And so we can just simply set these two expressions equal to each other, okay? And ultimately, what we want to solve for are going to be all of these, right? Okay. And so the procedure of transforming a distributed loading to a concentrated one is to form these two mathematical expressions and then use them to solve for the nodal loads. Okay, so everything I've circled here, these are the equivalent concentrated nodal loads. Okay. All right, and we can get their expressions depending on what our function is P of x, and also what our transverse deformation function is. Okay. All right. Any questions on this so far? Does this make kind of sense about how we're going to go about doing this?
Yeah, good question. So in this case, we just have two forces and two moments.
Yep.
But for the nodal loads, would it be just the sum of, I guess, the work done by each force or moment?
Yeah. So that's exactly what we have here. And so the total amount of work done is basically the sum of the works done by each of the individual nodal nodes.
And that would just be equal to the work distributed.
Yep. Yep. All right. And so the next question is, how do we actually go about solving this, right? Because the expression down here, we're basically done with that, and so we're not going to touch that anymore. Okay. And so the rest of the class we're going to be working on how do we actually evaluate this integral up here. Okay. So let's start with P of x. Okay. And so P of x, remember, this is going to be your distributed load. And for all intents and purposes, this is always going to be given to you You know, it's going to be given to you as you're solving your problem, but it's also just given by the finite element setup, right? And so a lot of times you're applying this load, and so you know, think back to your finite ANSYS adventures, right? And so this is something you directly apply into the software, right? Based on whatever physical situation you're trying to model. Okay, and so that's given, and so you know, we don't have to worry about that anymore. Okay, what we don't have is this guy right here. Okay. And so uy of x, this is a function, right? And so it's a function of x, which describes the transverse deformation of the beam. Okay. And so this is something that's totally new for us, because you know, we've mostly just been working with the discrete nodal deformations, right? And so we haven't really worked with a function like this. And so, you know, in order for us to actually use this work equivalent principle, we need a good expression for uy of x. Okay. Okay. And so that's what we're going to do. Right? And so we're going to look for a functional expression for uy of x. Okay. All right. And so how are we going to get this? And so recall, or maybe not recall, I kind of just mentioned this in passing last time, right? Recall that the element stiffness matrix for the beam that we're working with is based on Euler-Bernoulli beam theory. Okay. Okay. And so the simplest form of the Euler-Bernoulli beam equation is the following. Okay, so we have E times I times the fourth order derivative of uy with respect to x. Okay. And I'm going to do something simple right now where I'm going to assume the right-hand side is completely zero. Okay. All right, so we're not actually going to solve this, you know, but what we can say is that, you know, because we have this fourth order derivative, the simplest function that we can come up with to solve this equation is a cubic polynomial. Okay. And so let me write out the most generic cubic polynomial you can imagine. Okay. Okay. And so the most generic cubic polynomial is going to have these four terms, right? And so we're going to have a constant term, we're going to have an x term, we're going to have an x squared term, and we're going to have an x cubed term. Okay. And so this works out great, because, you know, we can see that if we differentiate this 4 times, then all of the terms can go away. And, you know, we're left with something that 0 is equal to 0, which works out. Okay. And so if you plug this directly into this equation here, okay, you'll see that it satisfies it. Okay. It's one of many that can satisfy, but this one works, and it's kind of the simplest one that we can come up with. Okay. All right. And so now the goal is, you know, how are we going to solve for each of these constants, right? Because we have A0, A1, A2, A3. Okay. And so the way that we're going to solve for these is that we're going to require this function here to match the nodal deformations on our beam. Okay. Okay. And so what does that mean? So essentially we're applying constraints onto this equation here. Okay. And so one such constraint that we're going to do is we're going to say that u1y, if we evaluate this at x1, and so we evaluate it at the left side of the beam, okay, then this has to equal to the transverse displacement at node 1. Okay. Okay. And so we say that uy of x1 is equal to u1y. And so similarly, if we evaluate this transverse displacement function at the other side of the beam, and so if we evaluate it at x2, then we get u2y. Okay, so that's the transverse deformation on the other side of the beam. And so now we have to factor in the nodal rotations, right? And so we have theta 1 and theta 2. And the way that those are related to the transverse displacement is we can take the derivative, okay? And so we take the derivative of uy of x with respect to x, and we evaluate that derivative at x is equal to x1, then we'll get theta 1. Okay. I think a small child just ran outside the classroom and was making a lot of noise outside. All right, and so similarly on the other side of the equation, we have du, or other side of the beam, sorry, we have du dx at x is equal to x2. This is equal to theta 2, okay? And so if we apply for these constraints onto our polynomial right here, it'll give us 4 equations that we can use to solve for our four constants, okay? And so I'll spare you the gory details of the math because we have plenty of gore to come, you know, with our own troubles. But you know, I'm going to go ahead and skip ahead to the solution on this one. But if you want to verify this in your notes, you can go ahead and do so. Okay. But I'm going to go ahead and skip ahead and just assume that we solve for, you know, each of these constants. Okay. Right, and then I'll give you the final expression on the next page, which is what we'll use in our problems. Okay. Right, any questions on this?
Yeah, just a quick one. The du over dx and the du over dy, is that just how it is?
Yeah, it's how the rotations are defined. And so the way the rotations are defined, it's defined as like an orientation of the beam. And so if you take the derivative of the transverse displacement with respect to the you know, the axial direction, then that gives you that exact orientation. Yeah. So you can almost think of it as like a shear string, and so that's essentially what we're evaluating. Yeah, it's not a compressive strain because compressive strain would be dux dx, but it's a shear strain because we're taking the derivative of a transverse displacement with respect to a perpendicular direction. Yeah.
And then you would do it on both directions.
Yes. Yeah. Mm-hmm.
Okay, thank
you. Mm-hmm. All right, and so let me go ahead and skip ahead to the solution. Okay. And believe it or not, it's not clean. Okay. All right, and so if we solve for our 4 constants, then we end up with the following expression. Okay. So the first thing we have is a square brackets, okay, and we have 2 over L cubed multiplied by u1y minus u2y plus 1 over L squared theta 1 plus theta 2. Okay. All of this is multiplied by x cubed. Okay. And so that was that entire thing right there. That was A3. Okay. Next we have minus 3 over L squared multiplied by u1y minus u2y. Okay. Minus 1 over L times 2 theta 1 plus theta 2 square bracket. So this is our x squared term. Okay. Plus theta 1 x plus u1 y. Okay. All right. So that's our deformation function, and so it's pretty gory. Yeah. All right. And so one definition here that we haven't seen yet is L, or we've seen L, but just to kind of make sure. So L here is the length of our beam. Okay. And the way that's defined here is it's x2 minus x1, right? And so it's the position of the right side of the beam minus the position at the left side. Okay. Right. So in case you're wondering where the L came from. All right. And so now that we have this expression here, we can go ahead and plug that in, and we can go ahead and we can use this to solve for work distributed. Okay. And because so remember, our work distributed. Okay, this is equal to integral. I'm going to change the integration bounds a little bit here. So instead of integrating from x1 to x2, I'm going to integrate from 0 to L. Okay. Okay, we have our load function p of x. And we have our transverse displacement function uy of x. Okay. All right. And so now we have everything that we need to solve for this, because we have uy of x. Okay. And so believe it or not, this long ass function right here, we're not actually done with it. We're actually going to integrate over it, right? And so we're going to plug it in here. Okay. And then remember, p of x, this is something that's going to be given to you in the problem. Okay. And so all you have to do is just multiply these two functions and then integrate it. Okay. And then that's going to give you first of all, it's going to give you a really long integral to do. Okay. And then when you set that equal to work nodal, okay, this equivalence right here, this will allow us to solve for f1y, f2y, m1, and m2. Okay. Okay. Remember, that's kind of what we've been after this whole time, is we want to take our distributed load and transform them into a set of nodal loads on the other side. Okay.
A question.
Yep. Mm-hmm.
So don't we already have f1y, f2y, m1 and m2, and then don't we want to find the displacements and the theta, the deformations and the theta?
So this is for a situation where you're not given f1y, f2y, m1, m2. So normally you are. And so for all the problems that I've given you up to this point, I've just given you the nodal nodes directly. And so what we're doing here is instead, if you're given a distributed load, you have to first transform that into f1y, f2y, m1, m2. Okay? And then once you have those nodal loads, then you plug those into a finite element direct stiffness method. And so everything that we've been covering today is kind of outside of the usual framework. It's just we're just trying to get up to the point where we can actually use our usual framework.
So my question is, do we need to, in order to solve for this large polynomial, do we need u1y, u2y, theta 1 and theta 2? We need numbers to put there, but we have not solved the whole system yet to find
so
those.
You're right. That's a good point. And so, I'm keeping them as u1y, u2y here because we just need them as symbols, actually. Because remember the expression that we had for w nodal, or w nodal was in terms of u1y, u2y, theta 1, theta 2. And so what you'll see from so we're going to do an example right after this, is that what you'll see from the example is that after we evaluate that integral, we're going to have a very long expression. And so we're going to have one term or one number that's going to multiply u1y. And so that number that multiplies by u1y, that's going to be our f1y, right? And so we're leaving the displacements in terms of symbols, because we haven't solved for them yet, but we can use them to kind of match up terms on both sides of the equal sign.
Got it. Thanks.
Mm-hmm. Okay, and so let's go ahead and do an example. And so this is going to take up actually most of our time today. All right.
Oh, just a quick question.
Sure.
Just going back to, I think I asked earlier about kind of like the sum of all the works.
Yeah.
you know? So in every case though, if you have a distributed load, it's always gonna break down into two transverse forces and two moments.
Yes. Yeah. Mhm.
You think?
Yeah, so this is strictly for beams. And so, yeah, if you're talking about like trusses and or even in the more general case frames, you would have a different breakdown. But this is strictly just for beams right here.
You think?
All right. So the example I'm going to do in class today is actually more difficult than the homework problem, just because I know these problems are quite a doozy. And so, you know, I want to do a fairly difficult one in the lecture, so that when you do the homework, it'll be a step down from this. Okay. All right, and so let's consider a situation where we have a beam selected to a ramp load. Okay. Okay. And so we have our beam. On one side, we're going to have node 1. On the other side, we have node 2. Okay. And so let's say that we have a pin support there and a roller support on this side, although, you know, for this case, it doesn't really matter. Okay. Okay. And our loading is going to be a linear function that starts out at 0 on node 1 and then ramps up in you know, in magnitude up until node 2. Okay. And so the function for this loading is going to be 5,000 times x. Okay. And the unit for that loading is going to be newtons per meter. Okay. So that's our load function. Okay. And so our load function is, you know, 5,000 times x. Right? And so the x is there because, you know, we have a linear, it's called a linear ramp. Okay. All right. And so given this nodal loading, what we want to do is we want to compute the equivalent nodal loads, okay, for this distributed load. All right. And so we have a lot of integrating to do. Okay. But first, let's kind of take it up from the top. Okay. And so when we have a distributed load like this, we're going to set up an equal sign. Okay. So we're going to say that work distributed is going to be equal to work nodal. Okay. And so let's go ahead and plug in our expressions for work distributed and work nodal. Okay. And so for work distributed, we have the integral from 0 to L of P of x, uy of x, dx. Okay. And so this is going to be equal to f1y, u1y plus m1 theta 1 plus f2y, u2y plus m2 theta 2. Okay. All right, and so now that we've set up this equation, we can just go ahead and focus on this integral. So I hope you like math because we're going to be doing a lot of math today. Okay. All right. And in fact, also for this problem, the L is going to be 1 meter, and so that actually saves us a bit of work. Okay. All right, so let's go ahead and start plugging in for this integral right here, right? And so we have an integral from 0 to 1 of P of x. Okay, and so P of x, we're just going to plug in straight from the problem. Okay, so P of x is going to be 5,000x. Okay, and then our uy, we're going to plug in our monstrosity from the previous page, right? So actually, let me draw a big parentheses around like that. Okay, So we have 2 divided by L cubed, okay, times U1y minus U2y plus 1 over L squared times theta 1 plus theta 2. Okay. And all this is multiplied by x cubed plus minus 3 over L squared U1y minus U2y but minus 1 over L 2 theta 1 plus theta 2 all multiplied by x squared plus theta 1x plus U1y. Okay. And of course, we're multiplying by dx. Right. Right. And so the next step is we're going to evaluate this integral. Okay, so I know it looks really scary. It's a lot of terms, but luckily a lot of them are just purely constants, right? And so you know, we have this 5,000 obviously is a constant, so we can pull that out of the integral. You know, everything in this expression here, you know, we're not integrating over any of that stuff, right? So we're integrating over x, and so that's also going to be a constant that we can just you know, that we can just pass on. Okay, and so the only things that you're actually integrating are these x terms. Okay, and they're just polynomial x terms. And so, you know, the integration itself is not difficult. It's not a hard integral to do. It's just a lot of writing that you just unfortunately kind of have to keep up with. So, you know, like I said at the beginning, you know, these problems aren't the most fun in the world, but and they're mostly just tedious. But you know, as long as you kind of do it slowly, you kind of do it step by step, then you know, it's not, you know, it's not so bad. It's better than you think, I would say. Okay. All right. Any questions on this so far? Okay. All right. So let's go ahead and start integrating. And in fact, you know, I'm gonna skip ahead in my notes a little bit, or not skip ahead, but simplify my writing, because since L is equal to 1, I'm just going to go ahead and plug all that in from there. Okay. So let's evaluate the integral. All right. So first thing I'm going to do is I'm going to pull out the 5,000. Okay. So the 5,000 can just come out there. Okay. I'm going to substitute L is equal to 1. Okay. And so if we do that, we get 2 times U1y minus U2y plus 1 over L squared, which is just 1. And so we have a plus theta 1 plus theta 2. Okay. Right. Previously, we had x cubed on this term, but because our p of x was 5,000x, I took that x and I distributed throughout the entire polynomial. And so now this term is x to the 4th. Okay. Right. Then we have a minus 3 over L squared, but since L is equal to 1, we just have minus 3 times U1y minus U2y. Okay. Minus 2 theta 1 plus theta 2. Again, I had a 1 over L term in front of that, but 1 over 1 is just 1. Okay. Okay. Then we're gonna have an x cubed in front of that term. Okay. Question. All right, and then we have the final 2 baby terms, right? And so originally we had theta 1x, but with an extra x that becomes theta 1x squared. And then we have U1y by itself. And so we multiply by x, we get U1y x. Okay. All right. So now that we've kind of cleaned up the expression a little bit, you know, now we're at a point where we can actually integrate. Okay.
Is the dx applied to all the terms there?
Yes, the dx is applied to everything.
Okay.
Mhm. All right. All right, so now we're ready to integrate, okay? And so remember, everything, all the constants in front of the x's, those are just constants. And so we can just bring them down throughout the integral, right? And so we don't have to integrate that. And so we have 2 times u1y minus u2y okay, plus theta 1 plus theta 2. Okay, we integrate x to the 4th, and so that's going to give us x to the 5th divided by 5. Okay, then we have a minus 3. Put a square bracket here. Minus 3 times u1y minus u2y. Okay, minus 2 theta 1 plus theta 2. Okay, then we're going to integrate x to the x cubed, excuse me. And so we integrate x cubed, we get x to the 4th divided by 4. Okay. Then we're going to integrate theta 1 x squared. And so we integrate that, we get theta 1 x cubed over 3. Okay, then we're going to integrate u1y x. And so we get u1y x squared over 2. Okay. And then we're going to evaluate this between x is equal to 0 and x is equal to 1. Okay. All right. And so we're lucky here with the integration bounds because one side is 0, right? And so since the lower bound here is 0, that's going to cancel out, basically this entire expression because we have x multiplied by everything here, okay? And so the only one you have to evaluate is actually just, the upper bound, which is x is equal to 1, okay? All right, so I think I have enough room to squeeze that here. And so if we plug that in, we get 5,000. Okay. Times 2 times u1y minus u2y plus theta 1 plus theta 2. Okay. We evaluate x cubed over 5 at x is equal to 1, and so we have times 1/5. Okay. Plus minus 3 u1y minus u2y minus 2 theta 1 plus theta 2. Okay. Okay, and this is going to be multiplied by x to the 4th over 4, evaluated at x equal to 1, so this is going to be 1/4. Okay. Okay, then we have theta 1 x cubed over 3, which we evaluate at x equal to 1, and so we just end up with theta 1 over 3. Okay, plus u1y times x squared over 2. So we evaluate that x at x is equal to 1, and we just end up with u1y divided by 2. Okay. All right. So a lot of calculations here, right? So as always, when you're dealing with one of these long calculations, just go slow. Don't. It's not a race. I think if or at least for myself, whenever I make mistakes on these kinds of problems, it's because I try to go too fast. Okay. And so take your time. Write out every single step if you have to. Because as long as you're kind of going at a slow pace and you're diligent and you're organized, you know, these problems, you know, you don't mess up these problems. They become a lot easier. Okay. Okay. And so the next step, you know, now that we're done integrating, right? And so we're completely done. The next step is going to be to combine the like terms together. Okay. And so I'll do that in 2 steps. And so I think it'll be easier to first distribute out all the terms. Okay. And then once we've done all the distributing, we can then combine the like terms together. All right. All right. Any questions on this? Okay. All right. So let's go ahead and do that. I'm still going to leave the 5,000 out there, and so the 5,000 is just chilling. Okay. Right, and so the first term we're going to have is going to be a 2 over 5 u1y minus a 2 over 5 u2y. Okay. Okay. And then we're going to have a plus 1/5 theta 1 plus a 1/5 theta 2. And so all of those are from the first term. Okay. Okay. Then we're going to have a minus 3/4 u1y plus a 3/4 u2y. Okay. Okay. And then we have the theta terms. So we have a minus 1/2 theta 1 plus a 1/4 theta 2. Okay. Okay. And then finally, we have the last 2 terms at the end, which is a 1/3 theta 1 and a 1/2 u1y. Okay. Perfect. Okay. And so from here, what we can do is we can combine the like terms together, right? And so all the terms that have u1y, we're going to combine together. Okay. And so whenever I'm doing a combination task, I always like to, you know, use colors when I can. Okay. But if not, you know, you can do this in stages. And so the way that I usually do this is first I'm going to bring down 5,000. Okay. Then the next thing we're going to do is we're going to we're going to write down all the terms that have u1y. Okay. Right. So we can see we have a positive 2/5. We have a minus 3/4, a positive 1/2. Okay. And so all these terms came from the blue circle terms. Okay. And so just to make sure that I don't double count these terms, I'm just going to cross them out. Okay. Next, let's write down all of the u2y terms. Okay. And so for u2y, we have these 2 terms right here. Okay. And so for u2y, we have a minus 2/5 plus a positive 3/4. Okay. u2y. Okay. And so just so I don't double count them, I'm going to go ahead and cross those out. Okay. For theta 1, I have all of those terms. And so I have a positive 1/5 minus a 1/2 plus a positive 1/3. Okay. Theta 1. Okay. Right. And then the last 2 terms, we can just read it off the table. We can just read it off whatever's left. Right. And so we have a positive 1/5 theta 2 and a positive 1/4 theta 2. Okay. Right. And then we have, and then that's that. Okay. All right, and so from here, it's just arithmetic, and so we can go ahead and combine these things together, okay? Okay. We're almost done, I promise. Okay. All right, so we have our 5,000 on the outside, okay? Okay, then we have a 3/20 U1y. We have a 7/20 U2y plus 1/30 theta 1 plus 9/20 theta 2. Okay. And so finally, what we can do at this point is we can finally multiply by the 5,000. Okay. And so if we multiply by the 5,000, what we get is 750 U1y plus 1750 U2y, okay, plus 500/3 theta 1 plus 2,250 theta 2. Okay. All right. And so you can see I've boxed that answer right there because we're basically done, because now that we've kind of combined this entire expression into something like this, we can just read off the coefficients in front of each term to give us the nodal forces. Right? Okay. And so the coefficient in front of U1y, that's going to be F1y. The coefficient in front of U2y, that's going to be F2y. Okay. The coefficient in front of theta 1, that's going to be M1. And then the coefficient in front of theta 2, that's going to be M2. Okay. Right. And the reason we have those is because, if you look at the form of this equation here that I've boxed, that's exactly in the same form as our expression for the nodal work. Okay. And so I'll write it down formally on the next page, but basically once you get into this form, you can just read off the coefficients and then you can be done. Okay. All right. Any questions on this, on how we arrived at this answer?
So those coefficients, those are the respective F and M's.
Yep. Mm-hmm.
Okay.
Yep. Okay. All right. So let me show you how these coefficients are that, right? Because remember where we started, right? Where we started was we said that work distributed, this is going to be equal to work nodal, right? Where for work distributed, well, we said that this is going to be the integral from 0 to L of P of X, Uy of X dx. Okay. And so this is what we've just evaluated. And so, the last 25 minutes of this class, we've been working on evaluating this integral right here. Okay. And if you think back to our expression for work nodal was F1y, U1y plus F2y, U2y plus M1 theta 1 plus M2 theta 2. Okay. And so that work nodal, that's just the definition of the work performed by our nodal forces. Okay. Right. And so now for the left-hand side of this equation, let's plug in exactly what we got, right? And so if we plug in, we get 750 U1y plus 750 U1y plus 1750 U2y plus 500/3 theta 1 plus 2250 theta 2. Okay. And so this has to be equal to this side of the equation right here. Okay. And so because we have our work equivalence, in order for these two to be equal, then F1y has to equal to 750, right? F2y has to equal to 1750. M1 has to equal to 500 over 3. And then finally, M2 has to equal 2250, okay? And so we can finally write out the answer to this. Okay. And so that's our answer. Okay. Okay. And so now that we have the nodal loads, now we can do our direct stiffness method, right? And so, you know, for any problem with distributed loading, you know, you're going to have to do a lot of work just to get the nodal loads, and then you have to solve a finite element problem on top of that. Okay, so it's it is quite a few calculations. Okay. But remember, you know, the one I gave you in the homework is a little bit of an easier expression than the one I have here. Okay? And so, you know, if you go through this example again and you really kind of understand every single step that we took, then, you know, the homework problem should be basically the same thing except a little bit easier. Okay. All right. Any questions on any final questions on this example here? All right, so we do have 10 minutes left of class, and so, you know, I don't want to shortchange you guys because you know, just because we have so much we need to cover in this class. And so let me give you a sneak preview of, you know, what we're going to cover Thursday, which is going to be a prelude to our activity on next Tuesday. Okay, and so this is like a preview of a preview. Okay. Okay. And so the subject of our next ANSYS activity has to do with unsteady or transient finite element simulations. Okay. All right. And so this is kind of a whole new thing. And so, you know, I know we've been doing kind of a lot of heavy math direct stiffness stuff, but now we're taking it back to ANSYS. Okay. And so, you know, besides the midterm that you guys are going to take, you know, before Thanksgiving, everything else in the class, you know, we're going back to ANSYS. And so side quest complete. So now we're back to the main story. Okay. All right. And so what are transient unsteady FEA? Okay. So let me start off by saying that, you know, for all the other ANSYS activities that we've been doing, and even for the direct stiffness stuff, you know, we've been working under the assumption that our structure is steady. Okay. Okay. And so, you know, if you think about, you know, whenever you start up ANSYS, the only analysis tool that we've been using is just static structural, right? So that's the only one that we've been using. Okay. But ANSYS is a much more diverse framework, or much more diverse program than just handling static situations. Okay. And so this will be our first foray into some of the other tools that are available in ANSYS. Okay. And so, you know, what's the opposite of a static situation? And the opposite of a static situation is a dynamic one that changes with time. Okay. And so because we have this new time element added to the, added to our, simulations, that's going to change things up. That's going to change things up quite a bit. Okay. Okay. And so before, when we would run a finite element simulation on a static situation, we would get a snapshot of the results. Okay. Right? It's like you took something, a picture on your phone, right? And so it doesn't change with time because it doesn't need to, right? Because nothing in the situation is changing with time. Okay. Right? And so for a dynamic situation, because the simulation is changing with time, now our results are going to be, essentially our results are going to be a video or a movie. Okay. And actually, the term that that engineers usually use for this is that we produce an animation. Okay, and so before we go further, I want to make clear that this is not the stuff that Pixar does with their stuff. Okay, so Pixar does something very, very different. But I'm using the word animation here to account for the fact that now our results they're actually going to move. Okay, and so because they're changing in time. Okay. And so this opens up a whole new host of possibilities for us, okay? And so that's not to say that static is limiting, right? So static simulations are extremely useful for a lot of situations, okay? But even so, there's a lot of engineering applications, there's a lot of engineering situations that need this time component in order to do an accurate simulation, okay? Okay. And so there's so many out there that require time to, right? And so, one application that comes up a lot in this class is, a lot of students, they want to simulate, if what's going to happen to a building when an earthquake happens, right? And so with an earthquake, you have a very dynamic loading, right? And so you have the ground that's basically shifting back and forth, right? And so there's no way that you can do an accurate earthquake simulation with a static, with static structure, okay? You can make some assumptions and you can do stuff, but it's never going to be quite the same without dynamics. Okay. Another situation, which is what we're going to do in our activity, is a car crash. Okay. And so if you want to simulate a car, striking an object, and then you want to see how that car is going to deform over time, you need a dynamic simulation for that because there's no good way that you can do that with statics. Okay. And so, for our activity next Tuesday, we're going to be simulating a car, and we're going to just ram it into a concrete wall, and we're going to see, how it survives, or I would say how it doesn't survive. Okay. Any kind of machinery, right? And so if you're working on, like an engine or something with a lot of moving parts, that's a very dynamic situation. And so if you want to simulate that, you can't do that with the static structure, okay? And so, being able to simulate these time-dependent phenomenon is, really important for an engineer, okay? It's really important, but, unfortunately, just because of the constraints of the class, we're giving this an extremely light treatment, okay? And so, one thought that I'll leave you with before we end today is that, the theory and the world of dynamic simulation stretches way beyond what we're going to cover in this class. Okay. Okay. And so we'll cover kind of the bare basics in this class, enough to at least get you started and to run kind of basic jobs in ANSYS. But there's it's almost like a whole nother method, right? And so it's still finite, and so you're still running finite elements, but you have to run almost an entire new set of theory on top of finite elements to account for this time-dependent phenomenon. And so it's in reality, you kind of need a whole class to really cover it all. Okay. And we do offer that class here. At least I think that's what they cover, because that's, just by judging by the name of the class, that's what they should cover. But I don't teach it, and so I don't know for sure. But the class, if you're interested in more of this, is EGGN 403. Okay. Okay. And the title of the class is Numerical Methods. Right? And so if you're interested in learning more about dynamic simulations beyond what we're going to cover in this class, I highly recommend that class. Right? It's a class that I've been trying to teach for years now, but because it's not an EGME class, because it's supplied by the dean's office, they don't give it to me because I guess the dean doesn't like me or something. But hopefully, I hope one day that I'll get to teach, because I love that class so much and I really want to teach it. Okay.
Do they utilize ANSYS in that class as well?
No, so they use MATLAB, and so so you learn about all these techniques through MATLAB. And so the thing with dynamic simulations is you kind of really have to dive into the code to really kind of understand what's going on. Yeah. Probably if I teach it, I'd make some connections to ANSYS. Maybe we'll do some activities from there, but the majority of the class is like MATLAB programming. Yeah. All right. Any final questions before we wrap it up for today? Would that qualify as an elective? Yeah, it should. Yeah, it's a 400 level class. It's a general engineering, and so it should apply for everyone. Yeah.
Yeah, it does. That makes sense.
All right, and so that's all we got time for. And so remember, your midterm project's due tonight, and so if you haven't turned it in, make sure you get that in before 11:59. Okay. And then on Thursday we'll pick it up here, and so we'll finish up the lecture notes on transient simulations. And then next Tuesday, we're going to be back on ANSYS, right? So have a great evening, everyone. Thank you guys for tuning in, and I'll see you on Thursday. Yeah.
Thanks, Dr. Tran.
Thanks, guys.
Thanks, Dr. Tran.
Dynamic simulation. Could we kind of also simulate how many cycles a component can withstand before it fails?
That's different. So that's called fatigue analysis, and so we'll cover that at the very end of class today too, because I think it'll be or the very end of the semester, because I think there's a lot of interest in it, and so that uses a different tool. But but the fatigue tool is a lot easier to use than transient ones, and so I don't have a full activity for it, but I do have a handout and like a short workshop on it.
And that's still considering the component actually.
So they do like an approximation for that, because in order to reach fatigue failure, like you have to run it like for sometimes like millions and millions of cycles, and so to simulate all of that is really taxing. And so then they do an approximation of all those cycles. So you can actually run fatigue straight from static structural, actually, so you don't need to do anything extra for that. But for the transient, you have to use a whole new set of tools for that.
Just another question, going back to the finding the forces and moments.
Yep.
So whenever we're given a distributed loading, we don't need to worry about the boundary conditions set by the plane of loading.
That's a good point. Yeah. So when you're given the distributed loading, the first thing you do is just convert it to the nodal modes, just like this. And so that's the first thing you do. But that's a good observation, because actually, because of the boundary conditions here, U1y and U2y should be 0 here, and so that should knock out everything. But the only reason I put the pins there is because I'm treating this as a standalone beam. But what you'll see in the homework is that I give you a beam segment that's not supported, and so you would do this first and then apply the boundary conditions when you do direct stiffness. Yep.
Professor, is it okay if I ask a question?
Sure. What's up?
In terms of the formatting of the report, is it okay if I kind of like space things out, because it looks a little weird when, let's say, the methodology is split between pages.
Yeah.
Like, would it be okay if I just bring it to the next page? Would that
Yeah.
mess up?
Yeah, that's fine. As long as
Okay,
the
perfect.
as long as the sections are there and they're in the right order, then you can space it out or format it how you want.
Okay, fantastic. It just looked really awkward, like not like when it was like split halfway. So I just want to ask.
Oh yeah, for sure. And actually
Okay.
that's really nice actually too, because then it's a lot easier for me to read when things are spaced out much more nicely. So yeah, so thanks for
Okay, awesome.
considering that.
Okay, thank you, Professor. Have a good night.
Yep, you too.
Yeah, I have a question about the format of the report.
Huh?
So I know a requirement is it has to be between 10 to 12 pages. Is that single spacing in terms like of line or
That's not a hard requirement, and so that's just an estimate, kind of just based on averages from the past when I've given similar assignments. But I'm not counting the pages at all. So just worry about your content, and then if it's under 10 pages, but all the content's there, then I'm not going to mark you down or anything. But if it's over that, then that's fine too. So it was just an estimate, because people usually ask me about how long I can expect.
Okay. And then one more question. I mean, I have everything done except for the abstract. So what's the difference between the abstract and the intro? Like I always get that confused like on my reports.
Yeah. So abstracts are usually like a 100-word summary of your entire report. And so your introduction the way I see it is the introduction kind of opens up the report. And so it kind of, gives some background information and kind of just gives it sets the table for the rest of the report. Your abstract kind of is a summary of absolutely everything. And so you have a little bit of your introduction there, of course, but you should also talk a little bit about your results too. And so you should talk about that, I ran the simulation and my stress was this, and so on and so forth. So the abstract is, it's for a person that doesn't have the time to read your whole report, but to get absolutely everything from the report and condense it down to 100 words, that's what the abstract is. Yeah.
Okay, I got it. Sorry, and then one more question. I know the exam or the midterm is coming up in a couple of weeks.
Mhm.
Like I'm a little nervous. Like I know it's not like a simulation. It's all like what we did these past couple of weeks.